So this will be the more mathy of the two talks. And I want to just go briefly, again, over what arithmetization is. This I mentioned in the past talk, so I'll just go over it quickly. I'm just repeating these slides. So we start, arithmetization is about starting, by the way, there'll be two parts. First of all, I'll talk about arithmetization, then I'll talk about Fry and polynomial commitment schemes. And again, this is more math. Not much in the way of proofs or formal things, but hopefully a little bit of intuition so that when you go and read for yourself, things will click. So arithmetization is this mysterious transformation that takes a problem about computation and for some obscure reason moves it over to a world in which polynomials over finite fields of low degree play a role. And that's very mysterious. And so we start with some problem, we reduce it to a bunch of polynomials and some constraints on them, and we ask the prover to give us a sequence of polynomials to commit to them by some way, and we need them to be of low degree, of a degree we specify to our liking, and we need them to be committed to, and only then can we do this magical thing of just sampling a random point and checking whether those constraints apply with respect to that random point. And this turns out to be the magic of succinctness. There is an additional piece of magic that gives you zero knowledge that is related to blinding, and I think it's very akin to the Shamir secret sharing. And I'm not going to explain that, both because it turns out to be slightly simpler, and also it's, there's enough here. But if you want privacy from polynomials, you also get that by other means. Good. So, arithmetization boot camp. So the goal is to see how polynomials give you succinct verification. So it's all about checking huge statements about a computation with the use of polynomials very succinctly, right? Like one random check, boom, we know it. That's the magic. And what I want to show to you is how polynomials give you that. A non-goal is to understand why, because I don't understand why. I know how it works, and I even know of a few generalizations that go slightly out of the world of polynomials, but like a deep understanding of why, I do not possess. There's a saying among mathematicians that you never understand math, you can only get used to it. So I think that very correctly describes my attitude towards things like polynomials and why they're used in these settings. Okay, I got used to them. I don't understand on a very deep level of why they're needed. And again, I want to emphasize, you can replace them with some things in some settings. You can take sometimes tensor codes of arbitrary things that are not polynomials. You can generalize to higher genus variants of polynomials known as AG codes or GOPA codes. And this is, again, all that we know to do today, but probably, in 50 years, when we'll meet here, there'll be some new things or some deeper understanding of why this works. So, and the way I'm going to go about it is basically run through a bunch of exercises or toy problems that we're going to solve, hopefully, together. And in all of them, again, the second part is going to talk about low degreeness and how do we check it, how do we get something like a polynomial commitment scheme. But for the first part, let's assume that we have an ideal polynomial commitment scheme functionality. So what does it look like? Alice, that is going to be the verifier later on in many of these settings, she's going to specify any field of her choice and any degree bound that she wants. She could do this more than once, like in these protocols. She can use several degrees. She could also potentially use different fields, but in our examples, it's going to be all over the same field. And then this ideal functionality has Bob transmitting to a trusted party that is not Alice, let's call him Tom. He transmits the coefficients of the polynomial, and they are only d coefficient. So it's a polynomial of degree at most d minus 1. And the ideal functionality makes sure that he has done this. And then Tom is fully trustworthy. And what happens is that whenever Alice wants, she queries Tom for the value of this specific polynomial at any point of her choice, and she will get the right answer. So let's assume we have this ideal functionality. And another thing in terms of cost, it costs nothing to Alice but for her interaction with Tom, or maybe also her interaction with Bob. So she needs to specify the field, the degree bound, and whatever she wants to query the polynomial, she needs to talk to Tom, send him the field element, get a response, and then do computations on her own. Okay? Now later on we'll see, of course we don't know of this ideal functionality. Probably if we had it tomorrow, then we would have the ideal proof system. Well, at least if we're using polynomials, right? Someone tomorrow might come up with an even more efficient scheme, for instance, that doesn't use polynomials. Okay, is this clear? And I want to make this very interactive. Yes?
Is there significance that Alice specifies F and D? If we just all agreed on one F and D that everybody will forever be using, would that somehow damage security?
Practically, well, first of all, it would definitely harm scalability. Think just about D, but also F. Yeah, like, what is the D that you choose? Like what, 2 to the 20? Well, what if I want to work with like 2 to the 30, 2 to the 50?
Sure, but from Alice's perspective, these are arbitrary values. Right? They're not part of a challenge or something. They don't take part in the security, right?
Well, they will play a part in the security. Like D will be, the higher D is, the lower the security is in some sense. But also, I should say that you can use algebra. Suppose you know there's some absolute, like just like we say 128 bits is what we'll ever need. You could say, no one will ever require degree more than 2 to the 100. So you could fix D. The field you probably don't want to fix, because there are all kinds of like symmetric cryptographers that come tomorrow with different fields that they say they want to use, and then you want to work over those fields, okay? Okay, any other questions about this definition? Cool. So now, algebra. I want to just present some definitions and some facts that we'll use, and they are relatively basic facts within the world of finite fields and polynomials. So first of all, let's fix a field, F, this funny font F. H is going to be a subset of F. For now, it's an arbitrary subset. And let us define the vanishing polynomial of H. Z sub H of X is the polynomial whose roots are precisely the elements of the set H with multiplicity 1. So you can write it down by just the product of X minus A for all A that is in the set H. So this is the vanishing polynomial. In a sense, it characterizes the set H, and sometimes in the literature, it is called the characterizing polynomial of the set H. Good. And here's a property that I'm not going to prove. It says that two things are equivalent. A polynomial has among its roots H, if and only if ZH is a factor of that polynomial. So let's first of all take an example, a very simple example that I hope you all know. A polynomial vanishes at 0, meaning P of 0 equals 0, if and only if you can write that polynomial as X times some lower degree polynomial. Similarly, a polynomial vanishes at the point 7 if and only if, meaning P of 7 equals 0, if and only if you can write P of X as X minus 7 times some polynomial of degree 1 less. Now, one direction is easy, because if X minus 7 is a factor, then clearly 7 is going to be a root, right? Because the X minus 7 part just is 0 on 7. The other direction is a basic property of polynomials over fields. Good. By the way, to those asking about rings or so on, it doesn't always happen in a ring, which is, if you want to generalize this stuff to rings, then you need to at least address the fact that it doesn't quite work in both directions. So again, we know that a polynomial vanishes at a set of points h, if and only if you can factor that polynomial into the product of two polynomials. One of them is zh of x. And another good thing to keep in mind is that for us, something equaling 0 is the good case. 0, having a root means it's like satisfying a circuit. It's like the circuit outputting 1. So 0 is good in the world of algebra. The second fact that we'll use is related to basically polynomials or their evaluations as error correcting codes. And it says that if you have two functions bounded by degree d, and they are evaluated over 100 d points, 100 is an arbitrary large number, you can replace it by something else, then if you sample a random point inside the evaluation domain and check if they're equal, your probability of seeing equality is less than the degree divided by the blow-up factor. And the reason is that two different polynomials of degree d can agree on no more than d points, which means that if you sample from 100 d points, then at most 1% probability that they will agree. Okay, so these are two basic factors. And now, assuming we have an ideal polynomial commitment scheme functionality, again, what are we going out to achieve? We want to achieve or to see how we can use these basic properties to have succinct verification of claims that involve very large domains. So the first example is all about algebra. So Bob has committed a polynomial to a polynomial commitment scheme, and the claim he wants to prove is that it vanishes on h. And for the purposes of this talk, think of h as being really large, let's say of size 1,000,000. So Bob claims that the polynomial vanishes on 1,000,000 points, and crucially, the degree can be much more than 1,000,000. Let's say the degree of this polynomial is 10 million. So if the degree was less than 1,000,000 and it vanishes on 1,000,000 points, then it must be the zero polynomial. But suppose degree d is 10 million and the size of h is 1,000,000, and Bob makes a claim. Well, remember that polynomial that I sent over to Tom? It happens to be one that vanishes among its set of roots is h. And now we would like to devise a succinct protocol for this. So we would like something that, if indeed p vanishes on all points in h, it will accept at the end of the protocol. And if there's even a single point, this 1 in 1,000,000 of the values is not 0, then it will reject with very high probability. Okay, so it's a non-trivial problem. For instance, I'll give you one solution that doesn't work. Let us sample a random point in h and ask Tom, the ideal polynomial commitment scheme entity, what is the value of the polynomial on that point. You can see that this will have very poor soundness, because if Bob is cheating and there's only one single point where p is non-zero on inside h, we just have a 1 in 1,000,000 chance of finding that Bob cheated. Okay? So the question is now posed to you. How are you going to use the polynomial commitment scheme and the two facts that we have here to devise a protocol that has very high soundness and perfect completeness and very low query complexity? We have like 50 minutes. Yeah. Yes?
Probably not going to be 0. No, it's probably not going to evaluate to 0 since it's a low degree polynomial.
Okay. But what does that prove? I'll be more specific. Suppose, again, the degree bound is 10 million. So even if you take the polynomial that does actually vanish on h, for instance, zh, on this random point it will not be 0, but it will still be something, right? Because it has only 1,000,000 zeros. So your random point the answer will be that it's non-zero. If you reject this, you have now violated completeness, because actually Bob was honest. Bob gave you a polynomial that does vanish on h. So, right, the degree is higher than the size of h. So there are many polynomials that vanish on all of h, but are non-zero on almost all points. I'll give you a hint. You are allowed to use the PCS again. You don't have to just have one use of the PCS. You can use it as many times as you want. Again, the communication will be counted. So the more times you communicate to Bob, the more times you query this thing, you pay for that. But you don't pay for whatever Bob needs to send to the PCS. I think now we have 48 minutes. Yes?
Maybe you could avoid even talking about the P and instead talk about Q the whole time. Like whenever you want to use P, just use Q multiplied by that thing number, right? And so maybe you don't even need to prove anything in order to...
Well, wait. Bob, just to make it a bit interesting, suppose that first Bob has committed to P. Now suddenly Alice, because she's, I don't know, she wants to cause him problems, she says, after he committed to P, she says, okay, here's your set H. And now something like this actually does happen later on in proof systems. You first commit to something, and then suddenly there's some randomness that takes constraints and throws something at you that if you're not satisfying all constraints, you will end up in a situation where not all of these H points are zero. So yeah, so Bob is already committed to P. Now H came along. How do we distinguish between good Bob and bad Bob? Now I like the direction of Q. That's good. And again, we can make it interactive. Just reminding you, we had this question whether protocols are interactive or non-interactive. So you can see that even if we're going to use at some point Fiat Shamir to make everything non-interactive, it's very useful to think about the interactive setting. Okay. Yes?
So if we want to verify that it's zero on a certain point, and we can multiply it with another random polynomial, and then we can just reveal it on that point, and if it's zero, then...
So what is the protocol you suggest?
Don't have to write a protocol.
Do we just need to verify the polishing alignment at the random point?
What?
Don't we just need to verify the polishing at the random point?
Okay, so what is the protocol?
So we have P commit to both commits to Q, and then Alice queries P and Q at the random point.
Yeah, that's exactly, I'll repeat the solution. So the protocol is, even if Bob is committed already to P, this is, I think, what you meant. Even if Bob is committed to P, Alice now says to Bob, you know what, Bob? Please commit to Q, in fact, in the right-hand side of fact 1. And actually, it must be of degree D minus the size of H. So now we're using this degree bound. So send whatever you want to Tom, your decision of Q. And now, so this was part 1 of the protocol. And now what the verifier does is she samples a random point in the field, and she queries both P and Q at this one random point. And then she needs to decide whether to accept or reject. So she accepts if the following thing happens, if A indeed is an instantiation of this case. Okay? This is the protocol. Now again, I just want to, we'll soon analyze its properties, but this is already 99% of the magic. Instead, we wanted to verify a claim about 1,000,000 points. We now have a protocol that just samples 1 point from 2 polynomials. And as you'll soon see, you have perfect completeness, and you have very good soundness, and it doesn't depend on the number of million. Even if this was a gazillion, you could still verify a claim about a gazillion zeros with just one query to each of 2 polynomials. And that's absolutely mind-blowing, and this is how you get succinctness. So let's analyze what happens. So Alice has made 2 queries to the PCS scheme. And in terms of efficiency, well, there's whatever cost the PCS costs. For now, it's 0, right? But let's keep that in the back of our mind, because this is going to be very important later on. And let's talk a little bit about the soundness probability. We'll leave the number of operations to the end, because, well, as you'll see now, it's actually not succinct. Why is it not succinct? this protocol? Where do the O of H operations come from?
Calculating a set of H, set H of alpha.
Yeah, so Alice needs, so there's one multiplication, but before that, she needs to evaluate ZH on alpha. And H is an arbitrary set of size 1 million, so the polynomial has, let's say, 1 million coefficients, and you need to compute all of them on the point A. So this is not yet succinct. But let's talk about the probability of error. So the claim is that it's D over F at most. And why? Here's a proof. Let's assume that P doesn't vanish on H. And again, even on one single point, it doesn't vanish. Well, we use fact 1, which implies that P of X, well, sorry, there's a typo here. It should be P of X minus ZH of X times Q of X. So I want a polynomial in X. So this polynomial is not the zero polynomial, but it is bounded by degree D, because this is degree D, this is degree H, and this is degree D minus H. And we rely here on the properties of the PCS. So this is a non-zero degree D polynomial, and now we use fact 0, which I'm not even mentioning here, but over fields, a polynomial of degree D can have at most D roots. So there can be at most D points where P of X equals this side, unless they're the same. That's it. So we have probability of at most D wrong answers. Again, this is a mind-blowing fact. This is how you get succinctness. Yes, sorry.
Yeah, can you relax the degree of Q requirement?
Yes. What will happen if you relax the degree of the degree of Q to D, the only thing will be that the probability of error will be D plus size of H over F. So to Tomel's question before, like, can we work with one universal D? Well, in certain cases, it actually makes a lot of sense to work with one D, as long as Q is very, very large. And then, yeah, you suffer a little bit, these factors of plus H. Okay? So you can. Everything will work, just your probability of error will be slightly higher, because this will now could be a polynomial of degree D plus H, as opposed to D. Yeah. Okay, so now how do we get succinctness? And for succinctness, it turns out that you need one more fact. That's enough. And it is that if H happens to be a multiplicative group, meaning it's the set of roots of unity of a certain order, then it turns out that ZH of X is the polynomial X to the size of H minus 1. Now, why does this help us? Because we immediately go down from H operations for computing ZH of A to log H, because we just need to do repeated squaring, right? So by now I can end this part of the talk, because you saw pretty much all of the tricks needed in order to get succinctness. Okay? This is how many of the systems are used. Up to the PCS, this is how Starks are built, and Groth 16s, and Plancks. They use these kinds of tricks. Now again, I explained how it's used. I don't know why, or at a deep level, why this is the case. Why is it that you have succinct representation for a multiplicative group? Why is it that polynomials have only D values and at a deep level? But it is useful. Okay. So next challenge. So far, yes?
Can you go through so can you explain again about the queries, who makes them, and what?
Okay, Alice or the verifier wants to make them. But we assume this trusted third party, this ideal functionality, Tom. So she makes the query. She tells Bob, send your commitment to Tom, but to the polynomial, first to P, then to Q. But she doesn't pay. Let's say that no one pays for that transmission. And then, well, actually, Bob is going to pay for it. But Tom is Tom is doesn't charge anything for that. And then Alice needs to pay for her queries to Tom.
And what equals for?
What?
What's the query?
Oh, she samples a field element. So depending what is the size of the field, it's log size of field many bits. It's very efficient. Usually you can make do with a 128 or 256 size field.
So she queries like this equation, like...
No, she queries P at the point. She sends 256 bits, and she gets 512 bits back. That's it, like in this ideal world. And then she does log of the operations over the field, and you're done in this ideal world. Good. So next challenge. So far, the claim I gave you was very algebraic in nature. Now we're going to use a variant of that is a little bit more computational. So this is actually a constraint that is used in all systems. Like, whenever you use Circom or Cairo or any one of these, a lot of constraints are of this form. This is a Booleanity constraint. You want to know that a field element happens to be 0, 1 valued. So it's a very simple case of range checking, and it's a very important constraint. So this is actually used a lot in actual proof systems. So now the claim is that P, that Bob is committed to, happens to have values only 0 or 1, even though it's a polynomial over the field F, and field F can be large. Bob is claiming that it has only the values 0 or 1 when it's evaluated on the set H. So, how are you? Okay, please devise a protocol for this. How much time do we have, by the way? 30 minutes. Good. So we have 30 minutes for this challenge. That's the correct answer. So we're going to do a reduction. We already know how to solve the question of whether something has zeros on H or not. And now we want to take something that has 0, 1 values and convert it to something, have a reduction to something that has zeros at the point H, if and only if the input had 0, 1 values at the point, at the points of H. And we use this constraint. So this is a constraint polynomial. It's a degree 2 constraint. And this is the solution. So once again, Alice instructs Bob, the prover, to send to the PCS a polynomial P, but we're going to allow it more slackness. So instead of bounding it by degree D, we're going to D minus H, as was the previous case, we're going to allow a degree 2D minus H because we have a degree 2 constraint. So degrees are going to blow up a little bit. So we tell Bob, please commit to some Q that has degree at most 2D minus H. And now we're going to just repeat the same process with the tweak that was offered here. So we're going to sample a random A just as before. We're going to make 2 queries, one to P, one to Q. And we're going to check whether the constraint applied to the answer. So if we take the answer, P of A, multiplied by 1 minus P of A, and subtract from that the thing that should be the factorization of this result into something that vanishes on H and something else, the quotient, whether that is 0. And now, assuming H is already a multiplicative group, we are in a world of very good efficiency. We have 2 queries, O of log H operations plus the cost of the PCS, and the probability of error is only 2 times D over F, and the proof is essentially the same up to this degree slackness. So let's just go over it very quickly. Assume that there's even one single point inside H on which P of that point is non-zero. Is not 0, 1. Let's say it's 7. Well, when we look at this side, when you apply 7, right, so P of that point is 7, so 7 times 1 minus 7 is not 0. Since that is not 0, we know that the polynomial P of x times 1 minus P of x just doesn't vanish on H. And then we use fact 1. We know that this cannot be the 0 polynomial, but it is a polynomial of degree at most 2D. So by the fundamental fact that there are at most 2D roots to such a polynomial, our probability of error is only 2D over the size of f. Now you've really seen, so it's the same trick, but now we saw how we can apply a range type constraint. And again, think of H as being like this immense, huge array. It's of size 1,000,000. Within 2 queries, we have extremely good confidence in whether all of these points in this array are 0, are 0, 1 valued, which is a very computational kind of constraint. Okay, now the only remaining missing thing, which is the next thing I'm going to show to you or give you, is how do we talk about the evolution of a computation? Because this is about some static array of size 1,000,000 that we just want to know that a constraint applies to each and every entry. But computation is about something that evolves with time, right? So there's like the current step, the next step, and we want to know that certain relations between the current, the next step, the third step apply. So how do we do that? That's the only remaining trick. Yes? What? Again? Gate proofs, maybe. I'm going to actually use, okay, I'll say the fancy name later. But here's a challenge. So I made up this computation. It's not a very interesting computation, but like think of it as this is some program that's at least non-trivial. So Bob is making the following claim. I know of a sequence of length h of bits, sequence of bits. And I know of an evolution of a computation that's described by the sequence B that satisfies the following things. So we start with, it's like a Fibonacci-like kind of computation. It starts with the first 2 elements of the computation being 1. Bob's main claim is that the very last element in this computational sequence is the answer to all questions. It's the number 42, modulo P, and like P is a fixed prime, and the field F is Fp. And the evolution of the computation is this very complicated thing where the next step, Bi, well, what is its value? You take 2 steps before, you raise it, you cube it, mod P, and then you add, well, depending on what the ith value of the array A is, you either add Bi minus 1 or you add nothing. Some weird computation. But it's not clear that for general P it's easy to solve. So Bob is making this claim. This is a claim about computation. This could be some hash function or something, and Bob claims that he knows a way to get a pre-image. So the question is, devise a protocol for this.
Sorry, B is public or B is part of the witness?
B, Bob is claiming I know this B, but for now, no. Well, the only thing public is the computations here. Well, B1, B0, B1, and BH minus 1 are public, so the 2 first things and what the computation should do. Right, but Bob is claiming, and for now we're focusing more on succinctness. You could also add zero knowledge to this and say, well, Bob wants to show that he knows this without revealing anything about A and B. We're not addressing that for now. It's just about succinctness. We don't have the time to read all of A and B. And we have this PCS. So, this is a very good exercise. I'm not going to show you the solution. I'll just say that part of the solution is that we're going to index the sequences. So Alice is going to think about indexing these 2 sequences, A and B, by powers of the generator G of the group H. So H is a multiplicative group. And think of, so Alice, instead of talking about A0, A1 up to AH minus 1, she thinks about A valued at the point, well, G to the 0, which is 1. And then the next element should be the evaluation of a polynomial at G, and then a G squared. That's hint number 1. And hint number 2 is that you're going to use more than one constraint polynomial. So we know already that for the polynomial that should capture A, we should use the Booleanity constraint that we saw. And this is a good exercise. And I'll mention to Gilad's question of what we're going to use, really what we're using here is yet another mysterious property of polynomials, which is that if you take a polynomial P of X, well, think of it being evaluated. And now you have this table of evaluations. And now if you shift things around so that you get the evaluation of P of, let's say, AX plus B for any affine transformation, that thing will still be a polynomial. So a different way to say it is that the that polynomials are invariant under affine transformations. They have a group of actions on them that you can use to move them around. And this allows you, at a very high level, to talk about the current step and the next step within a constraint, because you can think of the next step, P of x, I think of it as the current state, and P of, let's say, g times x would be the next step of the computation. So we're going to get these constraints that have inside them, polynomial evaluated at x, and some other polynomial evaluated at g times x, or maybe g squared x, or tomorrow it could be g squared x plus 5. So with these hints, those who want to solve this problem, there are 3 constraints really needed here, and one of them is of degree 3. But then you end up with a system with like 5 queries or so. It's a good exercise. So if you want, you can, I'll send also these slides. I'm not going to give the solution here, but you're going to use several constraints. You're going to shift things around using multiples of g, and you're going to bake like 2 or 3 constraints. And then you have a system where, assuming a PCS, you need only a very small number of queries. So again, those who want to try and solve this later on, take a picture of this and think about it offline. So now, how much time roughly do I have? Like 20 minutes or so? Good. So now we're gonna start opening this this assumed magical box that is the PCS, right? And because there is no ideal PCS. So this was the ideal functionality. And this is usually what a PCS actually looks like, yes?
So the thing we had before was FRI, or?
No. This thing, everything we did so far, assumed that you have an ideal PCS.
Right, but just in terms of like terminology, what was it called? Just arithmetization?
This is arithmetization. This, if tomorrow you arrive at the perfect PCS, like minimal cryptographic assumptions, minimal, commitment time, minimal verification time, works over all fields, like, then essentially this will give you, let's say, probably the ideal proof systems. Again, within the scope of polynomials. Then people might say, no, we want things that are not even related to polynomials. Yeah, so this is not Fry, this is just generic arithmetization. And in particular, all proof systems deployed over blockchain use these kinds of arithmetizations. And so less ideal and more messy real-world PCS will look more like this. Bob sends some commitment, some cryptographic commitment, and there's no more Tom around, so he sends it to Alice or posts it on a blockchain or something like that. Alice queries Bob, and Bob answers with the answer. And now there's some protocol. The protocol could be squashed. It could be maybe just a one-time proof send with it, a snark. But again, it's definitely in Fry, and I think it's easier to think about some interactive process that both parties interact in which, at the end of which, Alice decides whether to accept or reject. And what do we want? We want completeness. Completeness means that if indeed P is of low degree and its value is correct, then Alice will accept. You want soundness, which, that's practically speaking, you want the probability of accepting something that is false to be less than 2 to the...
False mean also high degree, only...
Yes, I agree. You're right. False is also high degree. So if P is not a good commitment, then yeah, you want efficiency, proving time, verification. Here's maybe... I wanted to also mention knowledge soundness somewhere here. So knowledge soundness would give you something stronger, which is like whenever the protocol succeeds with high probability, we actually know that there is a polynomial of low degree and Bob is committed to it. So that would also give you the low degree. Yes?
Is soundness even defined without that, like here?
Probably not. So, security, which crypto assumptions do you use? You would like universality if you can, all fields, maybe all rings. And now I want to describe Fry, and Dan is going to talk about KZG later on, then Planck, which uses KZG. So the Fry protocol was in a work with Ido Bento, Inon Choresh, and Michael Ryabtsev from 2018. And basically, the main things about it are that the proving time is O of D. Field operations, the verification time and number of rounds is O of log D. It's post-quantum secure under collision-resistant hash if it's interactive, or Fiat-Shamir for non-interactive, or random oracle model. And you actually get universality for all fields. So initially, we knew how to get Fry only for fields that have groups of like two smooth groups, meaning that the size of the group is divisible by high powers of 2. But now, recently, in this work with Dan Carmon, David Levitt, and Swastiko Party, we know how to get it essentially over all groups, over all fields. We don't know how to get it over all rings. It's another great question. Okay. So what is Fry? Fry is, well, first of all, the acronym. It stands for Fast Read Solomon IOP of Proximity. So let's first of all explain what an IOP is. An IOP is a model that generalizes the PCP and IP models. It's equivalent in terms of complexity classes. It is equivalent to NEXT, non-deterministic exponential time, which is equivalent to MIP and to PCP, but stronger than IP because IP equals P space. So for those of you who are into complexity theory, that's where it sits. And what is this model? It's an abstract theoretical model that is very convenient to work with, but not practical. To instantiate it, you need cryptography. But I should say that a lot of the analysis of Fry, well, okay, all of the analysis of Fry in the white papers works in this model. So there's no cryptographic assumptions, and it's information theoretic security. Okay. So what is this model? I like to imagine it as like a USB stick kind of model. So Bob sends a USB stick. Think of it as some Oracle, gives Oracle access to Alice. And Alice puts the USB stick on the table. Then she sends randomness. And Bob sends another USB stick, and she puts it on the table. And this goes on for a number of rounds, at the end of which Alice says to Bob, "Thank you very much, goodbye." She tosses a few more coins and makes some queries to the various USB sticks and decides whether to accept or reject. But the cost is only the cost of querying. It's the random access or oracle model. So it's the cost of specifying where she wants to read and then the bits read. So this is the abstract model. Now, what is Fry? It's an interactive oracle proof, IOP of proximity. I won't go into that here, but it's a type of an IOP. So there's the following problem. Given a subset S0 and a function F0 from S0 to the field, the prover is claiming the degree of F0. So F0 is a function. As a function, it could have degree as large as size of S minus 1. But the claim, the non-trivial claim being made, is actually that the degree is substantially smaller. Let's say it's at most 1/16 the size of the evaluation domain. So if we think of let's say the degree being 1,000,000, so maybe we get something evaluated over 16 million points, and the claim that Bob is making is that even though there are 16, this is a table of size 16 million, it actually describes the correct evaluation of a polynomial of degree only 1,000,000. So that's like the first oracle, the first USB stick sent in this game. And you can see that it feels a little bit like the PCS problem. Like later on when we'll instantiate it as a PCS, what Bob is going to do is basically send over a commitment, like a Merkle tree commitment, or a USB stick that includes the evaluation of the polynomial on the set of points S0. Okay, so that's looking ahead how we'll get a PCS from this. Now the Fry protocol just wants to distinguish between the case that the function f is indeed low degree and the case that the function f is extremely far from being low degree. I mean, if you think about it, it's very easy for Bob, for instance, think of the 0 function. So the 0 function is, of course, of low degree. Well, what if Bob sends a USB stick with the function being 0 everywhere but for 1 point? Okay, it's certainly not the 0 polynomial. In fact, as a polynomial, it has maximal degree because the number of zeros is, very large. However, For practical purposes, it turns out that what's written here is really the zero polynomial plus a little bit of noise that we can neglect. And it turns out that when you get to Starks or PCPs, this actually holds. It doesn't really matter if you have a few errors. So you really want to just distinguish between the case that something is a low-degree polynomial and very far from a low-degree polynomial. And that's what Fry gives you. So the way the protocol works is that we start with this function f0 being committed to. And now verifier sends a random x0. This is not the query. This is randomness that feeds into what Swastikopati calls a sketching, an algebraic sketch. It's a little bit like a hash. It's like a random hash. In fact, it is actually a random hash, and it's pairwise independent. So x0 samples a transformation that is 2 to 1 on pairs of points. So it comes from a class of these transformations. And what the prover is now asked to send is the result of this sketch or this hash, which is a function on half the size and should be of half the degree. And then this is repeated. The important things are that you have randomness, x0, that specifies which exactly kind of 2 to 1 hash you're using. But given x0 and a point down here below, there are exactly 2 points, and there's a partition. So for each point here, there are 2 points above, such that you know, once you know x0 and this point, you know which 2 points are there, and you know how should be the correct computation from these 2 points of this point. So there's a deterministic function that once you're given x0, the 2 previous values, you know what is the correct answer. This process is repeated logarithmically in d many times, each time shrinking the degree and the size until you reach something that is supposed to be 16 points, reflecting a degree of less than 1, which means it's a constant function. And then it's basically you're supposed to check that all of these different 16 points are the same. So once this commitment game has ended, so there's f0 and then f1 and then f2, and each time the size of these USB sticks decreases by a factor 2 each time. Once all of these USB sticks are on the table, now comes the part of verifying correctness. And what Alice does is she tosses coins and she picks a random y right here at the top. Given y, she knows what is its single unique neighbor. And these 2 neighbors, along with x0, which was used to sample the hash here, can be compared to the value that Bob is actually committed to. And now we take its neighbor again, and we do this thing again and again and again until we reach the root. And if all of these computations, the values we get are the values that Bob has committed to, then we accept. And otherwise, we reject. So the Fry protocol has a commit phase, which is interactive, and a query phase, which is basically just querying. So it's not that interactive. All the information is already there, and now you make these queries. And what Fry gives you is that the proof size is very efficient. It's at most 2 times the size of S0, because this is a geometric decreasing sum. So size of S0 plus half the size plus a quarter of the size, this thing is less than 2 times the size of S0. The verification is O of log S, which is O of log D queries. You have perfect completeness, and here's the soundness. So this is a theorem, and relating to Yuda's question previously, this is a proven theorem. We know that if f0 is accepted with probability 1/4, so 1/4 here is the square root of 16. So we know that if this is accepted with probability 1/4 plus something very negligible, then we can extract the polynomial of p of x of degree, the right degree, that agrees with f0 on sufficiently many points, on like 1/4 of the points. So there's a knowledge extractor here that operates efficiently given acceptance probability greater than square root of the rate. And the open question is whether the same thing or something similar to that holds not for square root of the rate, but for the rate. So again, going back to practical instantiations of Fry, all proof systems that use Fry, to the best of my knowledge, they work under the assumption or this security assumption that 1/16 is enough, which essentially means that each iteration of the query phase gives you log of the blow-up factor many bits of security. So here you'd get 4 bits of security. We don't know whether this holds. Maybe you only get, in this case, 2 bits of security, which means that maybe if this open question, by the way, that Starcore is going to be putting out a significant bug bounty or math bounty on resolving it. It's a very interesting question related to list decoding and error correcting codes. A very, very interesting question. Even if this is resolved in the worst possible case, in the case of, let's say, Fry and Stark, which says that this is the right answer, what you would want to do is double the number of queries to reach your target security, and there are no coding theoretic assumptions there. By the way, if Ethereum was in the business of giving precompiles for Starks, I would probably ask it to give enough of a leeway so that we can submit, let's say, proofs of twice the size so that we actually reach this safer bound. But now, the main downside of this approach is that even though here it's extremely efficient, this is extremely efficient in the IOP model where you don't need to use any Merkle trees, any commitment schemes, any things like that. But in reality, we do use Merkle trees to achieve these commitments, and then you actually get much, much longer proofs. Most of the size of this proof is the length of the authentication paths in the Merkle trees. And this turns out to be around, in the dozens to, let's say, 100 kilobyte range for typical degrees that are used in systems in practice, like, between 1,000 and, what is this, 1 trillion, like 1,000 times a billion, which is roughly the range where proofs are generated today. So that's the main downside of Fry. Okay, so this isn't a PCS. This solves a different problem, but you could wonder, how does one get a PCS? How much time do I have? Okay. Ooh, a lot of time. So maybe I'll actually prove Fry later. Yeah?
So now we learn how we can limit the degree, right?
Yes. What?
That's all we did with the Fry.
Yes, all we did was basically, well, it's a way to enforce a prover to commit to low-degree polynomials, and then verify whether it's some low-degree polynomial or far from any low-degree polynomial. But it turns out that even if you don't say PCS, this is enough to give you basically Starks and Snarks and ZK and versions of them, okay? But it's not that hard to construct some version of a PCS from it, so let me just specify it, for completeness. So how do we get a PCS scheme from this? So the only difference between this and a PCS scheme is that with a PCS scheme, we want to be able to know whether a particular value is the correct value for a polynomial. So first of all, we see 2 problems. Well, first of all, the evaluation domain can be much smaller than the field. And if we want to query about a point that is not in S0, then we have a problem. But we might be tempted to think that for values inside S0, this is already a PCS. How? We basically just apply the Fry protocol, and then we query at the point we care about as long as it's inside S0. So, question to you, why is that a bad idea? Why is it a bad idea to query the function committed to at any given point and trust that, even if the Fry protocol is accepted? Do you see an attack or counterexample?
Might have an error in that.
Exactly. Here's a concrete example. Suppose the prover wants to fool us. The prover knows that we're going to query at the point 7. And the prover wants to give us a value that is different from what the polynomial committed to is. So the prover is going to commit to a function that is 0 everywhere, but for the point 7, where the value is 7 as well. Now, when we apply the Fry protocol, as long as we don't query that one specific point, which happens with very small probability, we'll not notice its value. So we will accept this polynomial, and rightly so. This function is close to the 0 polynomial. But then when we go and query the point 7, we will get the wrong answer. So that's not a good idea. So any suggestions, how do we mitigate this? suppose the prover is committed to a function. We ask him, okay, what is the value of this polynomial at the point 7? We get the answer 7. What do we do? So what we do is this thing that is called sometimes quotienting. In the context of Fry, well, we first came the Fry paper, and then we had a modification of this that used these techniques. And we deliberated, and I think it was Swastik who said, okay, we know this thing must be called deep Fry. So, and then we found a way to open the acronym into the word deep. So what you do is basically, well, actually I noticed that it's written already here. So instead of applying Fry to the function f, after you asked about a and got the answer b, what you do is you modify the function to sort of quotient out by the answer given. So you subtract b from all values of f, so you reduce this constant. Now, if the prover was correct, we know there's a 0 at point a, which means that we can divide by x minus a, and we can locally do this operation. So instead of using the function f given to us, once we know a and b, we sort of in our heads have a new function that is just locally constructed from the original function. And it is the function that at point x is f of x minus b divided by x minus a. And what we do now is we apply the Fry protocol to this new function, and it turns out that this gives you a good PCS. So this is the end of this like deeper math talk. I'll just mention that the way Fry works is very much like a random folding of an FFT. So if you like FFTs, do check it out. You can also Google, like, there are a bunch of talks on Fry that like give some examples, and like I highly recommend Swastik Koparty's talk. It talks on this. He like gives a very nice explanation of the algebraic sketching and how it works. Yeah, I guess questions or yes.
And maybe for the last step, so FRI will make sure that F0 has low degree, right?
Yes.
And that, how is it enough to ensure that the value B was correct? Okay, so if the value B was incorrect, what happens then?
What happens then, informally, okay, formally to prove this is, okay, informally a good way to think about it is that suppose that f was actually a low degree polynomial, okay, or very close to it. So what happens is if b is not the correct value, when you look at f0, it is a non-trivial rational function. It is a polynomial divided by a low degree polynomial, and it's a good exercise to prove that this is extremely far, it is maximally far from any low degree polynomial. And the way to see it is assume there's some polynomial that's close to it, multiply both sides by x minus a, and you see that they're not the same. Now, this is just an informal explanation because the real proof is way more complicated. Why? We cannot assume, okay, generally when proving things like PCPs and Starks and Fry and so on, the soundness is the trickiest part. And when you deal with soundness, the problem you need to prove is not where the prover has picked a polynomial and evaluated with some noise, or not even when he picked a centroid that, of a ball that within small Hamming radius has a large number of polynomials that agree with it. The problem is that the prover can pick any undescribed function that is not close to any polynomial and still somehow mess with it. So all of the proofs of soundness in PCP world and in Fry world and so on, they require very deep math in order to actually do a decoding procedure, which gives you a knowledge extractor. What is actually proved is something way stronger. It says that if this protocol succeeds with non-negligible probability greater than square root the rate, then it means that the function f must be close to sufficiently close to a list of polynomials, and you even have an efficient procedure, it's called the Goswami-Sudan list decoder, to list decode those elements. So there's, and this is the way all soundness proofs work in PCP and by extension in Stark world. There's a lot of heavy lifting, mathematical heavy lifting, that works in the information theoretic world using a lot of algebraic coding theory and combinatorics in order to go a long distance about soundness. And just going back to why I like this line of works very much, it's like this elegance of the underlying math that also gives you very strong security. Because this is, in this model, it's even post-quantum secure, it's even secure against an arbitrarily powerful prover, as long as there's interaction and randomness. So because of that, you get very good security bounds, like based on a lot of math, and very minimalistic crypto assumptions, which I think is very important for, you know, the Lindy effect and long-term usability. Yeah. Yes?
I got a bit lost, and I think I was the only one. So I would actually ask this IOP will go in there. This to show that this function at the beginning, it is almost zero. Yes?
This IOP, it is to show that the function f is close to the valuation of some polynomial of degree at most d, not necessarily the zero polynomial.
Okay. And then how does this combination make it so that in the end, only from these last 16 entries, you can verify? Like, I mean, I see how you verify the past, but like this is the part that I kind of...
What you do with the last 16 elements, they should, in the good case, all be the same. Because by then you have reached something that is supposed to be a polynomial of degree strictly less than 1. So it's actually a polynomial of degree 0, which means it's a constant function. So really the full test basically also, let's say, reads the last 16 elements and makes sure that they're all the same. So like you check these different paths, and you make sure that they all end up in the same element.
So what is the combining step that allows for this to happen? Maybe this...
It's okay. I won't give the answer, but I'll give a pointer. You do the first step of an FFT, and you randomly combine the two elements. Like an FFT takes a function of size, you know, let's say S0, and breaks it up into two functions that are half the size and half the degree each, and then it repeats this. So what the Fry protocol does is it asks the prover to start this, and then using X0, take a random combination of them. That's how Fry works. So it takes, okay. Okay.
Okay. Are there any other questions offline? Let's thank Ellie.
Thanks.